What's up, boys and girls and everyone else? This is another science video lesson episode in chemistry for you. And for this episode, we will going to talk about volume, amount of gas in moles, and molar volume. Come join me today as we go over these concepts and find out what is Avogadro's law. Alright, so here we are in our lesson for this episode. So this is the Avogadro's law. Alright, so if you remember the previous episode in gas laws that we have covered, okay, so we have discussed already the first three measurable properties there. So we have the pressure, we have the volume, then we have the temperature. Alright, so the only thing that we have left behind, the only measurable properties we have left behind is the amount of gas. All right, so how is this amount of gas will fit in to our gas law? So what we have right here is the gas law, in which it explains how this amount of gas will interact or will be related to another measurable property, which is the volume. All right. So what you see on the picture right here is a modern way of administering anesthesia, okay, to a person. All right, instead of doing it by by injection or something like that, in the form of syringe. Okay, so instead, anesthesia was administered here through inhalation. Alright, so through inhalation. So the anesthesia is in a form of gas. Okay, so the more anesthesia that is pumped on this device that you have right here, it will have a greater effect. Okay, during the procedure. All right, so the patient will not feel anything. Okay, during the procedure. So I think this one is in dental laboratory or something like that, or dental clinic. Okay, so this is done first before extracting or removing a tooth, okay, from this patient. Okay, so this is one way of administering anesthesia in the form of gas. All right, inhalation. All right, so this particular example that we have right here is an real life application of Avogadro's law. All right, so let's discover in this particular lesson how is this Avogadro's law look like, or what is the concept behind this Avogadro's law. Okay, but before you go further with this video lesson that we have right here, so click the link above if you don't have any idea what are the previous gas law, okay, that we have talked about before this video. So the link is above. Okay, so it contains the Boyle's law, the Charles law, the Gay-Lussac's law, and then the combined gas law. All right, so let's get right into it. Alright, so if you're going to take a look at this statement that you have right here, 2 liters of carbon monoxide gas reacts with 1 liter of oxygen gas, and it yields 2 liters rather of carbon dioxide gas. Alright, so the question here is this statement true? Okay, by all means, is this statement true? Okay, so if you're going to take a look at the statement, so 2 liters and 1 liter of oxygen gas will produce 2 liters of carbon dioxide gas. How is that even possible? Alright, so how is that even possible? Is that even possible in the first place? Alright, so we have right here the complete chemical formula together with its balance form. Okay, how this particular statement will work. Okay, so with the use of this chemical formula that we have right here, we will be able to find out if the statement is true. Alright, so how is that possible? Okay, so literally, if you add 2 carbon monoxide and 1 oxygen, okay, basically, you will add up 3, right? So in chemistry, it doesn't work that way. Okay, it doesn't work that way. Okay, so there is a certain rule, all right, that is followed in chemistry, especially in the formation of chemical reaction. Okay, so in the chemical reaction, so there are certain rules, okay, like the law of multiple proportions, Okay, so something like that. Okay, law of conservation of energy or law of conservation of matter, something like that. So these rules must be followed in order for this one to be possible. Now, how is it possible that you have 1 liter and 2 liters of carbon monoxide gas and 1 liter of oxygen gas will produce 2 liters of carbon dioxide gas? How is that possible? Now, in this lesson that we will have right here, it will going to explain how is this possible. Okay? So, what is this Avogadro's law all about? Alright, so Avogadro's law was formulated by Amadeo. Alright, Avogadro, he's a Italian physicist. And what he points out is that at constant temperature, according to him, the volume of a gas is directly related to the number of moles. Alright, so that's his idea. So we produce here this formula that you have right here. Not only this particular statement, but also another hypothesis. All right, according to him, this is what this is infamously called Amadeo hypothesis. All right, this is talking about this hypothesis talks about the molar volumes. Okay, so the molar volume. So these molar volumes will be included in our discussion today. So let's try to find it out. So that is Amadeo Avogadro, the proponent of this Avogadro's law. Okay, so now according to him, that equal volumes of different gases contains equal number of molecules. Okay, so only when the condition is at the same temperature and pressure. So when the temperature and pressure is constant, the number of molecules that are found in your gases, alright, at equal volumes will be the same numbers. Okay, will be the same numbers as long as the temperature and pressure is constant. By the way, I forgot, Amadeo Avogadro is also the proponent of the Avogadro's constant. Okay, so this is the Avogadro's constant. If you remember, that is 6.022 times 10 to the 23rd power. Alright, so there's no unit on that. This constant that you have right here is used to describe the amount of particles, the amount of molecules, the amount of atoms, alright, present in 1 mole of any substance. Alright, so 1 mole of any substance, it might be an element, it might be a compound, something like that. So any 1 mole of these elements, compounds, or formulas, something like that, contains this amount of this constant that we have right here, the 6.022 times 10 to the 23rd. And this particular number is what he is talking about right here. Okay, the equal number of molecules. This is what he is talking about, that number. Alright, that number here. As long as the numbers, okay, as long as this gases contains equal volume, alright, equal volume, and it has the constant temperature and pressure, these numbers must be equal regardless of what kind of gas it is. Okay, regardless of what kind of gas it is, as long that this particular gases contains this equal amount of volume at constant temperature and pressure. Alright, so let's discover more about what is this Avogadro's law. Okay, so the first one that we have right here is the basic concept of his idea. The volume of a gas is directly proportional to the number of molecules of gas at the same temperature and pressure. Alright, so this is what it looks like. Okay, so let's watch this video from YouTube. Alright, so let's watch this video. I will provide the link of the video in this in the description below this video. Alright, so let's watch it.
Let's take a look at limiting reactants. Each of these flasks has 190 milliliters of one.
Although the topic here is about limiting reactant, but it clearly showcase, this particular experiment clearly showcase the Avogadro's law. All right, so
Molar acetic acid. How many moles of acetic acid is that? These balloons have differing amounts of sodium bicarbonate: 4 grams, 8 grams, 16 grams, and 32 grams.
Alright, so that is the amount of sodium bicarbonate present in those flasks that you have right there. Alright, so what is the liquid that you have right there? That is the acetic acid. We know that when acetic acid reacts with sodium bicarbonate, it will produce a carbon dioxide as its byproduct. Alright, so this is not all about the byproduct itself. It's how these balloons will look like after the chemical reaction. Okay, so let's take a look at the balloons that you have right here, and let's analyze, okay, and connect the idea of Avogadro's law in these balloons that you have right here.
How many moles of sodium bicarbonate are in each of these balloons? Can you determine the limiting reactant?
Alright, so this is the amount of moles, alright, that the sodium bicarbonate has. Okay, this is the amount of moles. And
acetic acid and sodium bicarbonate react in a 1-to-1 ratio to produce carbon dioxide.
alright, so this is the chemical reaction that you have right here. Okay, so I think the chemical equation is balanced already. Okay, in this case, so this is a combustion. Okay, combustion reaction because it produces carbon dioxide, and also this is a double displacement reaction in some cases. Okay, so
These
let's continue
and compare the sizes of the balloons. First, 4 grams. Next, 8 grams.
Okay, so as you can see, it has the sodium bicarbonate that was placed inside the balloon was different, or it is different in terms of mass. There are 4 grams, 8 grams, okay, respectively.
16 grams.
Alright, so we have here the 16 grams of sodium bicarbonate. Okay.
And 32 grams.
Alright, so as you can see, the balloons that you have over here, so okay, so I will just place myself here. Alright, so as you can see, the balloons that you have on this setup that you have right here, okay, what you notice is that the amount of sodium bicarbonate,
Sodium bicarbonate is the limiting.
alright, so the amount of sodium bicarbonate that you have right here, okay, has different is different in amount. Alright, so we have 4, 8, 16, and then 32. What you can see also is that the balloons are also different in sizes. So what does it mean? Okay, what does it mean? That the more sodium bicarbonate, alright, the more sodium bicarbonate the setup has, okay, so let's continue watching the video so that this balloon will be completely seen on the screen that we have right here.
Reactant. 1-to-1 ratio, the limiting reactant.
Alright, so there you go. So as you can see, the balloons have different sizes. Okay, so what does it tell us? Okay, what does it tell us? Does it tell us that the volume is directly proportional to the amount of moles? Okay, or to the amount of gas? Okay, so let's take a look. Okay, as the mass of the sodium bicarbonate increases, the size of the balloon also increases. So it means to say that the gas that was produced, so we have a constant here, okay? So the constant here is the amount of acetic acid, okay? So the constant here is the amount of the acetic acid. The variable that we have right here, alright? So the variable which is manipulated that we have right here is this amount of sodium bicarbonate. Okay, the amount of sodium bicarbonate. So as you can see here, the amount of sodium bicarbonate reflects the size of reflects on the size of the balloon. So it means that the greater the amount of sodium bicarbonate, the greater the amount of carbon dioxide that will be produced. Okay, because as you can see here, in a small amount of sodium bicarbonate, the amount of carbon dioxide okay, so if you were going to ask me how do I know that it is a carbon dioxide, upon looking at the chemical equation earlier, the only gas that is produced in the process is carbon dioxide. So there's no doubt about it that what is inside this balloon is carbon dioxide. Okay, so you don't need to ask anymore. Okay, what kind of gas is present here? Okay, all you need to do is to look at the equation and then find the gas that will be produced as a byproduct. All right, so as you can see here, in the smallest amount of sodium bicarbonate, it reflects that there is a small amount of carbon dioxide that was produced. All right, so meaning to say, small amount of carbon dioxide means a small amount of gas. Okay? So, meaning to say the carbon dioxide here that was produced is very small compared to 8, compared to 16, and compared to 32. Alright? So, 32 grams is far greater compared to the previous 3. So, it means that 32 grams produces a large amount of carbon dioxide gas. Okay? It produces a large amount of carbon dioxide gas during the process of chemical reaction. So it means that the larger amount of carbon dioxide gas, the larger the volume. It reflects the size of the balloon that you have right here. Okay? So it means that the number of moles, okay, the number of moles is directly proportional to the volume, okay, of that gas, okay, that will be produced. Okay, so the one that you have right here. Okay, so that is very logical. Okay, that is very logical. The more reactants that you have, the more particular product, okay, the more particular product that will be produced at the end of the day. Okay, so as you can see here, more carbon dioxide, increase in volume. All right, less carbon dioxide means less volume. Okay, so that was the very good experiment of Avogadro's law. Okay, so let's go back to our alright, so that was the direct proportion between volume and number of or amount of gas, okay, at same temperature and pressure. Alright, so the next principle that we have right here. Okay, 1 mole of any gas occupies the same volume for a given time or temperature and pressure. Okay, so it contains the same number of particles, atoms, and molecules. So what is this same number? Okay, what is this same number? This is the 6.022. This is the 6.022 times 10 to the 23rd power. Okay, that is the 6.022 times 10 to the 3rd power. It can be particles, it can be atoms, or even it can be molecules. Okay, so it tells us, this second statement tells us that in any 1 mole or 1 mole of any gas, alright, so 1 mole of any gas occupies the same volume. So what is this same volume? That's the question. What is the value of this same volume that we are talking about at constant temperature and pressure? And that was the molar volume. Okay? What is the value of the molar volume? That is 22.41 liters. Alright? So, in some textbooks, alright, it was 22.414, but for simplicity purposes, I just use until to the second decimal place. So 22.41. Now, this molar volume is constant if the temperature is at 0 degrees Celsius or 273.15 Kelvin and 1 atmosphere. Alright? So that must be, okay, this must be the pressure. Okay, not only 1 atmosphere, it can be 760 millimeters of mercury, 101.325 Pascal, 101.3 kilopascal, something like that. So, it must be constant, alright? These two must be constant in order to have a constant molar volume that you have over here. Okay? So, that is 22.41 liters in 1 mole. Okay? So, in 1 mole. So, if you were going to ask, okay, if I'm going to ask, what will happen if you increase the number of moles? What will happen if you increase the number of moles? Does the molar volume will increase itself? Alright, so let me know in the comment section below. Alright, so what is your answer on that? Okay, so definitely it will increase. Okay, so it will definitely the value of the molar volume will be completely different if you have greater than 1 mole. Okay, if you are greater than 1 mole or less than 1 mole, it should be 1 mole for you to have this constant value that you have over here. Okay, so the fourth one is some real gases at STP, okay, contains the same amount of molar volume. So as you can see here, oxygen gas, nitrogen gas, and hydrogen gas that you have over here, at STP, and all of them are 1 mole. Alright, all of them are 1 mole each. Alright, it contains, or they have the same molar volume. Okay, they have the same molar volume, although they differ in decimal places. Alright, but the molar volume itself, the amount or the value of the molar volume itself is completely the same. Okay, all throughout. Okay, all of these gases, despite that this is an oxygen, this is a nitrogen, and this is a hydrogen gas. As long that they are in STP and that is 1 mole, all gases, regardless of any kind, they have the same molar volume. Alright, so that was these are the 4 premises of your Avogadro's law. Okay, so let's take a learning check, okay, for this one. If you be able to understand what is this Avogadro's law all about. Alright, so this is the problem that we have over here. If 0.75 mole helium gas occupies a volume of 1.5 liter, what volume will 1.2 helium occupy at the same temperature and pressure? Okay, so the choices are 0.94 liters, the second one is 1.8 liters, and then the third one is 2.4 liters. Okay, so these were the choices. Okay, so before I reveal the answer, okay, so you can pause this video and you can work independently to find out which of the following here is the correct answer for this problem that we have. Alright, so let's analyze the problem. Okay, so we have here the amount of gas, 1, 2. Okay, and we have here the volume. And what we are looking for here is the volume. The final volume probably. Alright, because this one is the first amount of gas that you have right here can be treated as the N1, and 1.5 can be the V1. Okay, so what is missing right here is the V2. Okay, so what is this 1.2 mole? What is this 1.2 mole? This 1.2 mole is N2. Alright, so given the data that you have right here, alright, so given the data that you have right here, okay, so the conditions that we have here, okay, so the answer is 2.4 liters. So the answer is 2.4 liters. So how did we get this 2.4 liters? Okay, this is the solution. Okay, so we have here the data that we got from the problem a while ago. All right, so we have the formula that we were going to use. So now, if you were going to ask where this formula came from in the first place, this formula came from this formula. So V1 over N1 is equal to V2 over N2. So there you have it. Okay, so arranging this formula that you have right here. Okay, so if you arrange this formula that you have right here, it will arrive at the same formula that you have on this solution. Okay, now doing the correct math. Okay, so plugging the variables that you have on your equation, okay, and doing the correct math, it will give you the answer 2.40 liters. So 3 significant figure. All right, so 2.40 liters is the new volume of the helium. Alright, so this is the complete and correct answer. Alright, so 2.40 liters is the new volume of the helium. Okay, so Did you get the correct answer? So let me know in the comment section below if you get the correct answer. If you are confused on something, just put it right there. Okay? So just tell me what part of this particular topic that we have right here made you confused. Okay? So that is okay. So this is the Avogadro's law. All right. So this is the Avogadro's law in this working problem that we have right here. Okay. Alright, so let's take a look at the greater concept about the Avogadro's law. So this is the molar volume. Okay, so the volume of gases can be compared at STP. So what do we mean by STP? STP means standard temperature and pressure. Now, what is the standard temperature and pressure? So we have 0 degrees Celsius, or in Kelvin, that will be 273.15. Okay, so that will be 273.15. So the one that you have over here. All right, so next one, the pressure can vary, okay, depending on what unit are you using. So sometimes it is 1 atmosphere, and that 1 atmosphere is equivalent to 760 millimeters of mercury. That 1 atmosphere is equivalent to 101,325 Pascal. Alright, and that 1 atmosphere is also equivalent to 101.3 kilopascal. Okay, so those are the values of pressure in different units. So at standard temperature, alright, so this is the standard temperature that we are talking about. Okay, now at standard temperature, 1 mole is always equal to 22.41 liters. Alright, so 1 mole is always equal to 22.41 liters, and that is called the molar volume. Now, if you were going to analyze the balloons that you have over here, alright, so if you're going to analyze the balloon that you have over here, although they are made up of different elements or different compounds, alright, so we have helium, oxygen gas, and we have nitrogen gas over here. Okay, so hey, what do we have over here? Okay, what makes them what makes these gases contain similar molar volume? Number 1, they are 1 mole each. Okay, they are 1 mole each. All right, so how do we know that they are 1 mole each? Now, the molar mass of helium is 4 grams. So where is this 4 gram coming from? Okay, where's this 4 gram came from? It came from the atomic mass. Okay, the atomic mass of helium. Okay, next one, the molar mass that you have right here, the 32 grams. Okay, so this molar mass, okay, so this formula mass that you, or this molar mass, okay, we can use that one. Okay, this molar mass that you have right here is the, okay, we add up, okay, so we add up the atomic mass of the two the diatomic atom, or the diatomic molecules of your oxygen here. Okay, so that will be 16. Okay, 16 or 15.99 times 2, that will be 6, that will be 32. So here we are. So 32 grams of oxygen is equal to 1 mole. Okay, next one, the molar mass of nitrogen over here, molar mass of or atomic mass of nitrogen is 14 times 2. Okay, since that is diatomic, so that will be 28. Also is equivalent to 1 mole. Okay, so 1 mole is equivalent to an atomic mass of an element. 1 mole is equivalent to the molar mass of the element. Okay, now at standard temperature and pressure, all gases, regardless of what kind of gas it is, as long that it is a gas, okay, regardless if it is an element or a compound, they all have 1 equal amounts of volume, and that was 22.41 liters. Okay, we called it the molar volume. Alright, so that was the molar volume. Hey, so okay, now where can we use the molar volume? Okay, so where can we use the molar volume? Now, we can use the molar volume especially during the STP. Alright, so during STP, we can use the molar volume conversion factor. So the conversion factor that we have right here is 22.41 liters over 1 mole. Alright, so now what are the conditions of this one? In order to use this one, alright, so in order to use this, it should be at STP. Now, if it is not on STP, Okay, so what are we going to do? Okay, so if you ask, what if the problem is not in STP? What are we going to do? So you will use another technique. Okay, you will use another technique which is called the ideal gas law. Okay, so we can use the ideal gas law for that, and we will not discuss it right here. Okay, that will be a topic for another video lesson episode. Okay, so at STP, and you can only use this molar volume if you are dealing with problems related to gases. Okay, you can only use this molar volume that you have over here, this one, only if you are dealing with gases. This will not work on liquids. Alright, so this will not work on liquids or other type of matter, solid, something like that. It only works on gases. Okay, because liquids have different volume. Alright, molar volume, something like that. Okay, so that is the conversion factor. Let's put that one to good use. Okay, so what is the volume occupied by 2.75 moles of N2 gas or nitrogen gas at STP? So as you can see here, our problem is at STP, so we don't have any problems on this one. Okay, we will not have any problems on this. Okay, so the problem is asking us that we should convert this 2.75 moles of nitrogen gas to volume. Okay, so how do we do that one? Now, with the use of the conversion factor, we can do this one. Okay, we can do this one. You can also do this also by in reverse. Okay, you can do also in reverse. So, for example, the given is in volume, and the problem is asking you to convert it into moles. That is also possible using this conversion factor that you have over here. Okay, so let's take a look. So how do we answer this one? So with the use of dimensional analysis, with the use of the famous dimensional analysis, we will be able to solve this. All right, so this is the solution. So as you can see here, this is the conversion factor that you saw earlier. Okay, so this is the molar volume, and as long that you correctly placed which one will go on the denominator, which one will go on the numerator, you don't have any problem on this. So as long that you can cancel all the similar units that are found in your solution, okay, you are good to go. Okay, so we'll cancel out the moles that you have over here, and 2.75 multiplied to 22.41 liters, the answer will be 61.6 liters. 3 significant figure, and complete answer, 6.61 liters is the volume of the N2 gas. Alright, so that is the correct and complete answer for this problem that we have right here. Alright, so that is the use of the molar volume. Now, okay, so in order for me to know if you understand the whole concept correctly, okay, so again, these are the step-by-step. Identify the given, okay, write a plan, okay, so don't forget to write the conversion factor, the correct conversion factor, okay, so the correct form of the conversion factor, and don't forget to cancel the units that are similar in your solution, and that's how you find the answer to your problem. Okay, so let's try using that method here in our sample problems that we have over here. Okay, so the first problem is what is the volume at STP of 4 grams of methane, and the second one is how many grams of helium are present in 8 liters of gas at STP. Now, this problem is a bit tricky because instead of converting them into moles, okay, you are asked to convert mass into liters. All right, you are converting mass into volume. Okay, the other one is converting volume into mass. Okay, so is this problem solvable? Okay, can we solve this problem? Yes, using the conversion factor that I taught you earlier. Alright, so you can pause this video if you want to answer this one independently. Okay, and find out if your answer is correct. play the video. All right, so let's try finding out what is the correct answer. Is it 1, 2, or 3 in letter A and letter B? All right, so let's take a look at letter A. Okay, for letter A, the answer is 5.60 liters. All right, so or 5.59. Okay, so this is the answer. So 5.59 liters. All right, so what do we have right here? So first thing to do is you put your given. Okay, so in this case we have 4 grams of methane. Okay, so we have 4 grams of methane, and what do we have over here? Okay, so in order for you to convert it into the molar volume, or in order for you to do it or to solve this problem, you need to convert any mass. Okay, you need to convert any mass into moles first. Okay, you need to convert mass to moles, because that will not be possible if you don't convert that one into moles. Okay, so very first important rule here is to convert everything into moles. Okay, so we have here the molar mass of the methane. Okay, so 16. Where does this 16 came from? So 16, 12 for the carbon plus 4 for the hydrogen. Okay, 12 plus 4 is equal to 16. Okay, next one. We have here the molar volume, because the problem is asking us to convert mass into volume. Okay, so we have here the molar volume over here. Okay, then okay, it must be in moles. Okay, so it must be in moles. So your mass must be in moles in order for you to cancel this one out. Alright, so in order for you to cancel this one out and multiply it to the molar volume. Now, you can only use this one at STP. Alright, so at STP. You can only use this one at STP. Again, at STP. Okay, so now doing the correct math. Okay, so 4 divided by 16 times 22.41, you will get this answer. Okay, so you will get this answer that you have right here. So 5.59 liters of methane gas. Okay, next one, letter B. So this time, letter B is from volume to mass. Alright, so letter B is from volume to mass. So what are we going to do right here? Okay, so what are we going to do here? Okay, first is to convert. Okay, so first is to convert liters to moles. Okay, just like in mass, you cannot convert liters into mass if you don't convert it into moles. Alright, always convert it into moles first before converting it into mass. Okay, so how do you do that? If the problem is at STP, then you don't have any problem on that, because you can use this conversion factor, all right, for the molar volume. Okay, so this is the molar volume. Okay, and the one that you have over here is the molar mass. Okay, so the one that you have right here is the molar mass. Now, doing the math correctly, so we cancel out the liters. Okay, we cancel out the liters, then we cancel out the moles over here. And what we left behind is the mass. Okay, and doing the math correctly, 8 divided by 22.41 times 4. Where's this 4 coming from? That is the atomic mass of helium. That the answer will be 1.43 grams of helium. Okay, so that is the correct answer for letter B. That was number 3. Okay, so that was number 3. Alright, so that's how you use the conversion factor of the molar volume. Okay, so let's go now to the next part. Okay, now the volume or amount of gas at STP in a chemical reaction. So this time, okay, so this time we will now have the chemical reaction. Okay, we will now do the chemical reaction. Now, involving chemical reaction using gases is called gas stoichiometry. Alright, so that is gas stoichiometry. Alright, so now in stoichiometry, we determine the product. Okay, we determine which is the limiting reactant, which is the excess reactant, so on and then so forth. Okay, so now in this is gas stoichiometry that we have right here using the Avogadro's law. Okay, now in order to solve that one, the condition must be STP. Okay, the conditions must be STP, the standard temperature and pressure. So for temperature, it must be 273.15 Kelvin or 0 degrees Celsius, and for the pressure, it must be in 1 atmosphere, or depending on what unit you are dealing with. Okay, and the most important here is you must have a correct equation. Okay, you must have a correct chemical equation. Okay, because a correct chemical equation means a lot, as in a lot. Okay, and most importantly, aside from a correct chemical equation, the chemical equation should be balanced. Okay, so the chemical equation should be balanced. Okay, why is that so? Why is that so? It should be balanced because we should follow the law of conservation of mass. Alright, so the law of conservation of mass. No mass is created nor destroyed. Alright, no mass is created nor destroyed during the chemical reaction. Okay, so there shouldn't be interaction, or there shouldn't be another mass, okay, that will be introduced to your chemical reaction coming out of nowhere. Okay, so that is the reason why we balance chemical equation. So these are the two things, or these are the two things that we need in order to solve some gas stoichiometry problem that we will going to have after this. Alright, so let's solve some sample problems related to gas stoichiometry and Avogadro's law. Okay, so what do we have right here? The volume, or what volume of oxygen gas is needed to completely react with 15 grams of aluminum at STP. Alright, so in this case, we need to provide the first one, chemical equation. Okay, we need to provide chemical equation. Okay, so the chemical equation for this one is aluminum reacts with oxygen gas. Okay, aluminum reacts with oxygen gas, produces aluminum oxide that you have over here. Okay, so this is the aluminum oxide. Now, how did we get this chemical formula? So how did we get this chemical formula? Now, the aluminum has +3 charge. Alright, so the aluminum has +3 charge. And that is why it belongs to group 3A, something like that. Alright, we have the oxygen. It has -2. Okay, it has -2 charge. So if you crisscross them, alright, so if you put it right here and you put the +3 over there, so you will have your chemical formula like this. Okay, now the chemical equation is correct. How about the balance equation? Okay, so did we balance the equation correctly? So we have 4 aluminum here. We have 2 times 2, we have 4. So aluminum is balanced. And we have the oxygen. So 3 times 2, 6. Alright, so 3 times 2, 6. So 2 times 3 over here on the product side, we have 6 as well. Okay, so definitely we have the correct balanced equation. Okay, so this is one important. Okay, one of the most important thing that you should do. Now, what if your equation and if your equation is not balanced and your equation is incorrect? What will happen? Okay, your answer will be incorrect as well. Your final answer, which is the volume, will also be affected. So your answer here, this volume depends on this. Okay, so take note, always take note that the answer that you have over here, that the answer for you for this problem depends on this equation. Okay, if you have a wrong equation, then you might have a wrong answer. Okay, so if you want to independently solve this problem on your own, okay, so you can pause the video, then play the video again if you want to know what is the answer on this problem. Alright, so let's answer this problem. So I have already provided the solution, okay, for this problem. Okay, so the first one is to convert grams or mass of aluminum to the liters or volume of oxygen gas that will be produced. Okay. Now, as you can see here, we in this chemical equation, the only gas that is produced is this one. Okay? So, this particular problem doesn't deal with solid respectively. It doesn't deal with solids. Okay? So, we are looking for gas. Okay? We are looking for the answer, and the product must be in gas form. Okay? So, as you can see here, we planned out everything that you have over here on this side. Okay? And we just used the dimensional analysis. Okay? So we just used the dimensional analysis. So, we plot out the given. Okay? So, what did we have? What do we have here first? Okay, so what do we have here first? Okay, so we have here first the molar mass. Alright, so the molar mass of aluminum. Okay, so that's the molar mass of aluminum. So how do we get the molar mass of the aluminum? So we get the molar mass of the aluminum using periodic table. So that's the atomic mass of your aluminum, 26.98. Alright, next one. So where this, you should know before you enter. Okay, so before you enter the process, you should convert mass to moles. Always remember that. Now, what if it is in liters? If it is in liters, you should convert it first into moles. So don't ever forget that one. All right, so where's this one came from? This one. Where's this coming from? Okay, it came from the formula itself. Alright, so it came from the chemical formula itself. So that is the reason why your chemical formula or chemical reaction rather, chemical reaction, that's the reason why your chemical reaction must be correct. Alright, must be correct. So that whatever you put here at the middle, okay, so whatever ratio that you put here at the middle will not affect your final answer. Okay, so what do we have right here? This 3 is this one. Okay, so okay, and the 4 that you have over here is this 4 that you have on this chemical reaction. Okay, so okay, do not expect that it is always on the reactant side. It might change. All right, so it might change in some situation. So we are just fortunate that this ratio that you have over here, this ratio, is coming from the reactant side. Okay, so this ratio that you have over here is coming from the reactant side. Okay, so it varies a lot. Okay, so it will vary depending on what kind of problem that you are dealing with. Alright, and the last that you have over here, okay, the last that you have over here is the molar volume conversion. Alright, so this is the molar volume. Again, we have the molar mass, we have the ratio, which comes from the chemical equation. So then don't ever forget this one. That comes from the chemical equation, and we have the molar volume. Alright, so if you're going to ask, can we interchangeably, alright, so can we interchange this process that you have over here? Yes. Okay, you can always change, you can interchangeably do this process. Okay, but it always depends on the problem. Okay, so it always depends on the problem. Okay, so doing so, let's cancel the units. So grams over here, cancel. Moles of aluminum is also cancelled over here. Moles of oxygen gas is also cancelled. Then at STP, so we are left with liters. So that is what we are looking for. So this is the correct answer and complete answer as well. 9.34 liters of oxygen at STP, or 9.34 liters of oxygen is needed to produce to react on 15 grams of aluminum, okay, at STP. All right, so that is the answer to this first problem, okay, for gas stoichiometry. Okay, next one. Okay, so the next part is what mass of iron will react with 5.50 liters of oxygen at standard operating procedure. All right, standard temperature and pressure. All right, so this is the chemical formula given to us. Okay, this is the chemical formula, and first thing to do is check out the chemical formula. Alright, or chemical equation. Okay, so let's check out the chemical equation if it is correct. Okay, so the first one is iron. Probably the one that the iron that is used here is iron 3. Okay, so iron 3. Alright, and we have here oxygen. Okay, so when these two reacts together, we have iron 3 oxide. Okay, doing the crisscross, so iron has plus 3 charge because it is iron 3, not iron 2, and the oxygen is we have negative 2. So doing the crisscross, alright, so doing the crisscross properly, then we will get this iron 3 oxide. Okay, so is it correctly balanced? So 4, then 6, 6. Okay, so that is balanced correctly. Then therefore, our chemical equation here is correct. We are now ready and good to go. Okay, so let's take a look. So we are asked to convert the volume into mass. Okay, we are asked to find out what is the mass of the iron using the volume of oxygen that you have over here. Alright, so again, you can independently answer this question. Okay, so you need to have your periodic table. Okay, so you need to have your periodic table here. Okay, so okay, what is the answer to this question? Okay, so I have already prepared the solution and the answer to this question a while ago. So first thing to do is to plan out. Okay, so first thing to do is to plan out what we are looking for. And by the use of the dimensional analysis, we can cancel units that are similar and find out the correct unit that we are looking for. Okay, so we have the given 5.5 liters of oxygen. And what do we have right here? Now, in the previous problem, the molar volume is on the opposite side. Okay, this is on the last side in the previous problem. So this is now the molar volume. So, don't ever forget, okay, so let me remind you again for the last time that you should need to convert liters to moles before entering this process. Convert liters or convert the volume into moles before entering this process. Okay, so the one that you have over here is the ratio. Okay, so the ratio found on your chemical equation. Okay, so this is the ratio found on this chemical equation. So 4/3. Okay, so we have the last one. This is the molar mass. Alright, so this is the molar mass of your iron. So iron's molar mass is based on its atomic mass, which is 55.85 grams. Okay, so that is the molar mass of your iron. Okay, there you go. And cancel all the units. Okay, cancel all the units. And what do we have right here? Okay, so what do we have right here? Now, when you cancel all the units, do the math correctly. 5.5 divided by 22.41 times 4 divided by 3 times 55.85, you will get the answer of 18.3 grams. Okay, what's the correct answer? 18.3 grams. Okay, 18.3 grams is needed in order to react to 5.5 liters of oxygen at STP. So that is the complete and correct answer. I repeat, 18.3 grams is the mass of the iron needed to react to 5.5 liters of oxygen at STP. Okay, so that was the molar volume in gas stoichiometry. Okay, so before we go to more sample problems, we have more sample problems that we have right here. Always remember, before you go to certain process, okay, before you go to certain process, you need to convert mass to moles, and respectively, you need to convert liters to moles. If you don't do that, you will not be able to do this process correctly. And most importantly, you need a correct and balanced equation. Okay? So that is the most important thing that you need, right, in order to solve this problem. Correct, balanced equation. All right. So that's for the sample problem, or so that is for the example that we have right here. Let's go now to more sample problems related to Avogadro's law. Okay. Alright, so here we are in sample problems related to the Avogadro's law that we have discussed a while ago, that we have in this video lesson. Alright, so we will work on some problems that is related to that, and try to find out what are the possible problems that we might encounter, okay, in our exams or in our other things that that uses or that might use the Avogadro's law. Okay, so the first problem that we have right here is the basic idea of the Avogadro's law. Okay, that the volume is directly proportional to rather the amount of gas, or the N. All right. So in this case, let me read the problem. 5 liters of gas is known to contain 0.965 moles. If the amount of gas is increased to 1.80 moles, what new volume will result if the temperature and pressure remains unchanged? Okay, so again, these sample problems that I have right here, you can work on it independently by pausing the video before I reveal the answer. Okay, so let's take a good look on this problem. So let's write first the variables present on this problem that we have right here. Alright, so okay, so the first one is we have here the 5, and we have here the 0.965, and we have the 1.80 mole. Alright, so we are asked to find out the new volume. So probably this one is the V1. Alright, so liters. So the final volume, or the V sub 2, is missing. Alright, next one we have N1, which is completely associated with V1. Okay, so we have 0.965 mole. And we have the 1.80 mole as the N sub 2. So 1.80 mole N sub 2. Alright, so in order to solve this one, we will going to use the basic formula for the Avogadro's law based on Avogadro's idea, which is volume is directly proportional to amount of gas. Okay, so V1 over N1 is equal to V2 over N2. Alright, so but before we go to solve, or but before we go even further solving this problem, let's take a good look on what answer do we expect. Okay, what answer do we expect on this problem? Okay, so the first one is let's take a look at this 2. Okay, we know that N sub 2 is greater than N sub 1. Alright, N sub 2 is greater than N sub 1. So we mean to say that V sub 2 should be greater than V sub 1. That is our hypothesis. Okay? That is our hypothesis here. That V sub 2 should be greater than V sub 1. If the idea was directly proportional, volume is directly proportional to the amount of gas, it should be. Okay? It should be greater than V sub 1. V sub 2 is greater than V sub 1. Alright. So since V sub 2 is missing, so this is the formula that we will going to use. N2 over N1. Alright. Now, let's plug in the variables that we have on our data. So, we have 5.00 liters times N2. We have 1.80 mole over 0.965 mole. Okay, so we got cancelled here. Okay, so we will cancel this one. And using our calculator. Okay, so we have 5 times 1.8 divided by 0.965. Okay, so the answer is 9.34 liters. Okay, 9.34 liters is the new volume of the unknown gas. Unknown gas. Right. So that will be our okay, so this will be our answer for this problem. Complete complete and correct answer. Alright, so that is the complete and correct answer that we have right over here. Okay, so is our expectations correct? Okay, that the V sub 2 should be greater than V sub 1. So, it is. Okay, it is correct. Okay, so if this is less than the V1, we have a problem. Okay, we have a great problem here. Okay, so that is 9.34 liters. Okay, so that is for the problem number 1. So did you get the correct answer? Okay, so if so, okay, let me know in the comment section. Okay, what is your thought? What are your thoughts? Okay, on getting the correct answer. Okay, next one. Okay, so this is a very tricky problem. Okay, aside from very long statement, it has a very tricky things on its sleeves. Okay, so a cylinder with a movable piston contains 2.0 grams of helium. Okay, at room temperature, more helium was added to the cylinder and the volume was adjusted so that the gas pressure remains the same. Okay, so we have here, the pressure remains the same. Okay, how many grams of helium were added to the cylinder if the volume was changed from 2.00 liters to 2.7 liters if the temperature was held constant? Okay, so the temperature here was held constant. Okay, so pressure and temperature were held constant, so we don't have any problems at this one. Okay, now what are we going to do here? Now we have two volumes. Probably this will be the V1. Okay, so 2.00 liters is the V1 and the V2 is the 2.70 liters. Okay, now what will be our ends? Okay, what will be our ends? Now in this problem we don't have ends. Okay, as you can see, the only thing that we see here is the 2 grams over here and nothing else. Alright, so the 2 grams that you have over there. Now, what are we going to do? Is it the end of the problem? No, we still have possible ways, or we still have a possible way to solve this one. We need to convert this into moles since we have a given element over here, or a given compound or element. In this case, we have helium, that is an element. Okay, so upon looking at the periodic table, the helium has a 4 grams of atomic mass. Okay, so we will convert 2 grams into moles. So 2.00 grams times 4.00 grams of helium, 1 mole. Alright, so cancel the grams and we have 0.500 mole of helium. Okay, so there we go. And the thing here is, if you read the problem thoroughly, the problem is asking how many grams, not how many moles. Okay, not how many moles. How many grams were added? Alright, so were added. Okay, so that's the question here. So let's try and find it out. Okay, so let's try and find it out. So we will use this formula. V1 over N1 is equal to V2 over N2. Okay, now let's have first the expectations, okay, for this answer. Okay, if V sub 2 is greater than V sub 1, if V sub 2 is greater than V sub 1, then definitely N2 should be greater than N1. Okay? If it is directly proportional, N2 should be greater than N1. Okay? So that is our hypothesis. Okay, so let's move forward and solve this one. So since N2 is missing, so N2 is equal to, okay, N2 is equal to V2 times N1 over V1. Okay, so that is the formula here, and we'll plug out, or we'll plug in all the values that we have over here. Liters, then we have the 0.500 mole over, okay, so over we have 2 liters. All right, so with the use of our calculator, okay, so we have 2.70 times 0.5 divided by 2. Alright, so the answer will be 0.675 mole. Okay, but the question is not looking for moles, it is looking for grams. Okay, but before we convert it into grams, let's take a look at our answer. Is our answer greater than N1? Okay, is our answer greater than N1? Then, definitely, we are correct. Okay, it should be greater than because directly proportional. Okay, so volume is directly proportional to the amount of gas. So we are correct. Okay, now we can change this one into grams by doing it in the conversion factor. Okay, so 0.675 moles of helium times okay, so we have 1 mole over here. Alright, so 1 mole and we have 4.00 grams. Okay, so the answer will be your possible mass that you have over here, the possible mass that you have will be 0.675 times 4. So that will be 2.7. Okay, 2.70 grams. Now, the question is, how many were added? This is not what we are looking for. How much were added? So, this 2.70 will be subtracted to the 2.00 grams that you have over here. Okay, so 2.70 minus 2.00. So, the amount that were added is 0.7 grams. Okay, so the amount that was added is 0.7. Alright, so 0.7 grams is the amount of gas added. Alright, so this is the correct and complete final answer. Okay, so for this problem, so 0.7 grams is the amount of gas added to this container. Okay, so that is sample problem number 2. So did you get the correct answer? Okay, so if so, let me know what are your process that you used, or what are the process that you used in order to solve this one, which is different from the one that I have right here. Okay, let's go now to the next problem. Okay, so this is, I think, the last problem that we have right here. Okay, so in this case, we will going to use gas stoichiometry over here. Okay, so consider the following equation. So this equation is the equation used to transform the nitrogen dioxide into N2O4. Okay, so what is the problem? So if 25 ml of nitrogen dioxide is completely converted to N2O4 gas under the same conditions, what volume will the N2O4 occupy? What volume of the N2O4 should possibly occupy? Okay, so again, you can pause this video and answer this problem independently. Okay, so the first thing that you need to do is convert the units that are not in the standard unit that we will going to use in this problem. So the first one is 25 ml. Okay, so 25 ml is converted into liters. We were going to divide it by 1,000, so that will be 25 over 1,000. So that will be 0.025 liters. Okay, so we are now good and ready to go. Okay, so what is completely converted to N2O4 gas? So 0.025 liters of NO2. Okay, and we were going to convert it into the volume. Okay, the volume of N2O4. So how do we do that one? Okay, so the first one is the molar volume. Okay, so we have 22.41 liters and 1 mole. Okay, so that will be 1 mole. And on the middle, the ratio of this equation. Okay, so since this is balanced already, so 2, 4, 4, N2O4. Okay, so that is balance. So since this is NO2, alright, so NO2, so we will put NO2 here to cancel it out. Okay, and the one on top is the 1 N2O4. Alright, then multiplied to, going back again to the molar volume, since we are looking for the volume only, so we are not looking for the mass, so volume again. So we can use 1 mole of N2O4 over here. Okay, and on the top, okay, so on the top is the 22.41 liters. Okay, so we can cancel now. Cancel this one, cancel this one, and cancel this one. Okay, then what we left here is the liters. Okay, so the liters, which is the corresponding volume of the N2O4 that will occupy. So the volume that will occupy is, let's use again the calculator. Okay, so 0.025, okay, liters divided by 22.41, okay, divided by 2 times 22.41. Alright, so the answer will be 0.0125 liters, or that will be 12.5 milliliters. Alright, so let me see if I'm correct. Times 1,000. Alright, so 12.5 milliliters is the volume that the N2O4 occupy. Alright, so this is the correct and complete answer to this problem that we have right here. Okay, so that is the gas stoichiometry problem. Okay, now in order to solve this one, the problem should be at STP. Okay, the problem should be at STP. If the problem is not on STP, that will be a topic for another day. Okay, so that will be a topic for another video lesson. That is the ideal gas. That is the formula, or that is the idea that is used to compute or to solve problems related to gas laws that are not in STP. Okay, so that's the ideal gas law. Okay, now we have here the Avogadro's law in real life. Okay, real life application. So the first one is the air pump that we have right here, that used to inflate balloons, all right, and ball that you have right here, and also tires. Okay, now logically speaking, the more air that you pump on this basketball, the more air that you pump on this balloon, the more volume thus the balloon and basketball will increase. Alright, so it tells us that the more air, the more amount, or the greater the amount of gas that you put inside these containers that you have over here, then definitely its volume will also increase. Okay, next one, breathing. Breathing is one example of Avogadro's law. So when you inhale, the volume of your lungs increases, so therefore the volume of oxygen gas also increases on your lungs. When you exhale, the volume of carbon dioxide lungs from your lungs decreases. All right, and the gas itself, the carbon dioxide itself, is also decreasing. Okay, so that's how it works. And we have here the one of the famous example of Avogadro's law, or one of the famous application of Avogadro's law, is in the airbags. Okay, modern day vehicles have airbags on steering wheel, on the dashboard, on the side panels that you have here on the doors. All right, so it contains an airbag, and this airbag contains a compound called sodium azide. Alright, so the compound named as sodium azide. Okay, it has a formula of NaN3. Alright, so that is the formula. And this sodium azide is being directed to inflate. Okay, to inflate immediately the airbag before your head hits the steering wheel or the dashboard or the side panels that you have right here. Okay, it will be inflated faster before your head hits everything inside the car. Okay, so how does it work? Okay, let's watch this video coming from the slow-mo guys. Okay, so you can subscribe to their channel. Okay, so I will put the link in the description below this video so that you can visit them and watch their video about this airbag anytime. Okay, so the question here, how fast the airbag deploys? Okay, so let's watch. Alright, so now let's watch their video about how the airbag deploys. Okay.
Hello, internet.
Hiya, how's it going?
You asking me or the internet?
I don't care about you, so I'm asking.
I assume they're fine because they're watching the slow-mo guys video
Big time.
on the internet.
Well, today we've got a car airbag, haven't we?
I was always amazed that when an airbag goes off in a car, in the steering wheel, I thought, how does the airbag not hit the driver in the face?
Yeah, I
when
just put it like a big smack
how
in
does
the
it
face.
just deploy in his face? And it turns out airbags deploy so immensely fast that usually they're fully out and inflated before the driver has even moved from the impact. So let's see how fast that really is by filming it at 2,500 frames a second in HD with a Phantom Flex.
Alright, so in this
Got
case,
batteries here, gonna connect them up and hopefully that'll
okay,
work.
so in this experiment or in this demonstration that they will do, they will show us, okay, how the airbag deploys, okay, how fast the airbag deploys, and they will use a slow motion camera, okay, for us to appreciate how it deploys. Okay, so let's take a good look on that.
But I'm a bit scared about this one, to be honest.
All right, Dan. Wear this for safety. You don't. I'm a bit scared. All right, go for it. Huh? Go for it. Hey, that was fast.
Oh my god.
Bloody heck.
Do you see me jump?
No.
Hit myself.
Alright, so that's how fast the airbag deploys and the reaction of the sodium acid. Alright, so the reaction of the sodium acid compound inside this airbag is super fast. Okay, with the help of the computer sensors, okay, with the help of the sensors that leads to the computer box of the vehicle, okay, if there's a collision, this sensor will detect and activates the airbag and deploys it immediately before your head hits anything inside the car. Okay? Alright, so that's how fast it deploys. Okay?
Oh,
Whoa.
that's far. Touched it.
Alright.
It was actually really.
So we're gonna try and drop.
Okay, so even when you drop something and the sensors detect that there is something changes in the pressure, okay, around the vehicle, so the airbag will definitely activate. So let's watch it again.
Holy crap! Oh my god!
Okay. Alright, so that was the... Okay, so that is the immediate deployment. Okay, so that's the immediate deployment of the airbag once it detects. Okay, once the computer or the sensor detects any changes in the vehicle, it will detect and deploy immediately that airbag to prevent injury. All right, so that is one of the profound and most real life or realistic example or application of Avogadro's law in real life. Okay, so these are some examples, and to end up our video lesson about Avogadro's law, so we have a summary right here. In Avogadro's law, the volume of gas is directly proportional to the number of moles of the gas. as the number of moles increases, the volume will also increases, as the picture tells us. Or even if you are inflating a toy balloon, you will also notice that relationship. Okay, next one, we have as the temperature and pressure remains constant, then therefore the formula should be like this. Okay, V1 over N1 is equal to V2 over N2. And more so, since we talk about molar volume and gas stoichiometry, a mole of any gas occupies the same 22.41 liters at standard temperature and pressure. Now again, what is this 22.41 liters? This is the molar volume. Alright, so this is the molar volume. So always remember, that is always in STP. Okay, that is always in STP at 1 mole. Okay, so that was the Avogadro's law. Okay. And that ends up our topic for this video lesson about Avogadro's law. I hope you'll be able to get value on the topic we discussed today. And if so, don't forget to like this video. If you have questions and suggestions, write them down in the comment section below this video. It will help me a lot in the algorithm for my YouTube channel. Most importantly, don't forget to subscribe to my channel and hit the notification bell for you to be updated for more science video lessons like this in the future. I'll see you next time, everyone. Enjoy learning and practice always. Stay safe and peace out.
Bakaみたい子供なのね